Good morning, everybody, and or good afternoon, depending on where you are in the world. This is Jeremy Grimshaw. I'm one of the leads of BESSI. We're delighted to welcome you to this seminar today. We'll give people another minute or two to start off or to join us, and then we'll get going. But really good to see people joining today. And we're delighted to see Atli Freitime, who's just celebrated his birthday this week. Happy birthday, Atli.
Thank you very much. I can also add that I've been suffering from COVID this week, so there's plenty of reason to give me attention and thoughts.
Okay. Why don't we get going? Because I'm sure people will continue to join us, but we've got a lot to get it through. So I'm delighted to, well, actually, Susan's saying just if people want to put their cameras on just now so we can see what a lovely group of people we have, that would be good before we sort of kick off. And welcome to everybody. So I'm going to share my screen and just have a brief introduction about BESSI, and then we're going to go into the formal presentation today. So just want to do that. Hopefully you can see my slide deck. So this is actually our third BESSI webinar series. And we're going to run a series of webinars between now and the summer. Just so you know what BESSI is, you can see it stands for Behavioral, Environmental, and Social and System Interventions. And we established BESSI because really BESSI interventions were the cornerstone of the global response to the pandemic. From the earliest days, we were asking individuals and societies to change their behaviors, their systems, to reduce the risk of infection whilst we're waiting for effective vaccines and therapeutics. But even as as we're very aware now, we're having to continue this sort of focus on BESSIs as new variants come up or new waves emerge. One of the challenges here, though, is that we have an imperfect evidence base on the effects of BESSIs for infection control. And in the first year of the pandemic, less than 5% of the global COVID-19 research budget was focused on BESSIs. We recognize that we need a range of different methodological approaches, and this seminar today is a great example of thinking through what methods will best answer the question. But just as one example, our colleague Paul Glasio has been basically keeping an eye on how many trials have been conducted of COVID interventions, and you can see that there are over 2,500 drug trials that have been registered. But only 18 BESSI trials, and that is quite a remarkable distinction or differential, recognizing that there are many other types of research that we actually need to address the agenda. Whoa, what are we doing? Okay, sorry about that. Beyond the pandemic, this area of research is still highly relevant. Existing infectious diseases, whether they're endemic, seasonal or periodic outbreaks, are a major cause of morbidity and death globally. And BESSIs are also our main defense across ID outbreaks, although we might use different BESSIs if we have something spread by the oral fecal route rather than an airborne route. So we really need to develop both a BESSI research agenda and a BESSI community to improve response to the current pandemic and prepare for future outbreaks. Some of the challenges are whoa, okay. The BESSI research is inherently interdisciplinary. We need to bring together disciplines that may not have traditionally worked together. And that raises challenges, particularly if we're trying to get new BESSI research off during a pandemic when everyone is really working at the limit of their capacity. So what we're trying to do is sort of think about how do we build those teams? Can we build those teams outside of infectious disease outbreaks? How do we actually advance a global BESSI research agenda, so both during this pandemic but future outbreaks, we have a better evidence base to help inform decision makers. So I'm delighted to welcome our speakers for today. I'm doing a really bad job with my slide deck. I do apologize to people. Not quite sure why. I'm not normally this ineffective. Anyway, we're delighted to welcome Dr. Andy Conway-Morris and Andy Turner to present their work. The reason we really liked this study was we thought it's quite methodologically innovative, both in terms of the design and how the outcomes were measured. It also was a beautiful example of this need for interdisciplinary working. That Andy Conway-Morris could not have done this without Andy Turner, and probably vice versa. And we've only got 2 members of the team, and the whole team, I think, has got a much wider range of disciplinary perspectives. So again, it's a really good example of the kind of way we need people to come together. So I'm going to very briefly introduce our 2 speakers and hand over to them. So Dr. Andy Conway-Morris is the lead author on the paper we're going to discuss today. He's an MRC clinical scientist at the University of Cambridge and a consultant in intensive care medicine in Addenbrooke's Hospital, UK. He was saying before he came on, his main interest has been actually about diagnostics and pneumonias, and somehow he fell into this as a research field. So he may actually tell us a bit about that. And then Andy Turner is the coordinating authorized person for heating, ventilation, and air conditioning for the Cambridge University Hospital Addenbrooke's Trust. So he came from the sort of the ventilation side, I mean, a couple of things again. Andy says this is the first time he's given a webinar, so he's a bit nervous, but I from the few minutes that we've talked about, he's got a lot to say already. So I'm going to hand over to them in a sec. What they're going to do is talk for probably sort of 25 to 30 minutes. Then we're going to have a discussion period, and Susan Beakey, my colleague, is going to lead that. What we'd like to do is, as we're going through the webinar, could you put questions in the Q&A, sorry, in the chat box, and then we'll kind of come back to those at the end of the presentation. So that's all I had to say just now. And so Andy Turner is going to go next. So Andy, if I can hand over to you, and looking forward to what you've got to say.
Okay, thank you very much. I'm just going to do a small PowerPoint presentation, and I'll just talk you through that. Let's just do this quickly.
That's great. We can see that, Andy.
Okay, I just need to get onto this slideshow. There we go. Right. So in January 2019, I was approached by a company called Filtrex, who had a solution to change a normal room or a side room with natural ventilation into a negative or positive pressure room using an air scrubber. They were going to use this system. This machine was actually, it was of interest to me because it had a pre-filter, the HEPA filters, and UVC technologies. At the time, I was intrigued because we were struggling to provide good negative pressure side rooms, and NHS England came to us to, they were trying to find out how many hospitals could provide negative and positive pressure side rooms. So what we did is, Filtrex had already completed a specific particle test done at St. Bart's Hospital in London, and they'd used a company that does all our verifications for ventilation called Approved Air. And the results that they got from the particle counting and the smoke testing was actually pretty good. So in theory, they had this machine that kind of said what it could do on paper. And those are the results there. I still struggle to understand how these machines would benefit the trust, because we still use natural ventilation and forced air ventilation, which everyone deemed as still being sufficient. So I asked my seniors if I could purchase a machine just to trial, but they didn't understand the benefits. They were virtually unknown, so people were skeptical. They kind of thought it was just a money making gimmick at the time. So I had a company who had supplied us with temporary air conditioning systems because the hospital's really old. We don't have comfort cooling on all the air handling units. So there are certain areas that get really hot in the summer. So we have to get temporary air conditioning systems in. So basically asked this company to source me an air scrubber, something that was a lot less expensive and a lot smaller than the Filtrix unit. Medtronics at the time, they found this little machine from Maxback. It's made in Switzerland. And they gave it to me for free and said I could use it to my will, which I was quite impressed because funds at that time was quite limited. So the thing is, the trials that I started to do on my own, I did in my own spare time. People were saying that this is a pipe dream, and it's a waste of time. So in my lunch breaks and in out of hours, unpaid weekends, I came in and started to do all the testing myself because I was really impressed by the capabilities. There's some more information on it. And I then decided to convince my boss to pay for a particle test, the same particle test that they did at St. Bart's by the same company, because they understood exactly what was required. So I chose a live environment. I didn't want to have it in a lab or an environment that was put together for the test. I wanted to test it in a live environment. So I took it to the welding bay down in the States, which was absolutely filthy. And we had guys welding and grinding and doing whatever it is. And we did the test. And this little machine, after 5 minutes, gave us incredible results. They were removed particles. I think it's one of the tests was 22 million particulates, and after 5 minutes, it reduced it down to 700,000. So I was quite impressed with that. So, and that's the positions where they were tested. It was quite a large area. So I thought, well, okay, this machine may work. I then took it to, I approached infection control, the head of infection control, and we took it down to a clinic where we tried to do plate testing. It didn't work at all. We couldn't get any sort of result from the plate testing. And I just thought, well, if we can't really prove that these do what they say on paper, I don't think the clinicians are going to want to use them, because they're very, very skeptical. Everyone was skeptical about air scrubbers at the time. So at the time, NHS England approached us again, and they wanted us to provide magnehelic gauges for all the negative and positive pressure rooms within the hospital. And so I spoke to my AE, my authorizing engineer, and he said to me, listen, you need to come up with a bespoke idea that's going to be really easy to use. So I designed a system. I contacted a company who then approached Dwyer in America, and they produced this for me. So I had color indicators, which is basic for any staff member to just have a look at, to glance at it and go, green for go, red for no. And those are the two positive and negative pressure gauges. So anyway, what I did, I started deploying them through the hospital. And that's how I met Dr. Vilas Nevaperkar. He was interested in creating an ICU hot chest facility where patients, because at the time they'd already gone through the first wave of COVID, and when they were bronching the patients, a lot of the staff members felt really unsafe. So they wanted to create this area where all the 4 rooms that you can see are negative pressure rooms, and I was installing the magnehelic gauges in there, and got chatting to Vilas, and he gave me this idea. And so we created, this whole test was based on this hot chest ICU originally. Infection control got involved, and all the microbiologists, because this was going to be quite a result for ICU, where the patients could come in, get bronched, and then whether they were positive or negative, because they never knew at the time, they could go to a negative pressure side room where they wanted it to be pathogen-free and bacteria-free. So Vilas was talking to me, and I went home that same night and I was thinking about it. And behind the scenes, I was testing this air scrubber, and I knew that this would potentially work in this environment. So I came back the next day and I spoke to Vilas. I said, listen, I've got a solution for you. I've been testing this air scrubber, and I had to explain exactly how it worked. And, because some of these clinicians aren't very technical. And he was very, very interested. He then set up a meeting with Professor Gordon Dugan, who works at the university, has won all these fancy awards for, his work. And we sat down and we had a layman's chat. And he asked me to explain because my boss at the time was, she wasn't happy about the time that I was spending on trying to create this system. So she came and sat in the meeting, and they asked me to explain my methodology in layman's terms, which I did. Gordon was really impressed, and Vilas as well. And from that period, they decided that we had to go ahead with this because it was a no-brainer. The only problem is we just didn't know how to test to see how, well, actually which pathogens, bacteria and fungi were in the environment, in the air. And it was really important, I think, for Vilas and for everyone else to understand that not all environments are the same, and therefore you have to prove what's in the air in that specific environment to then be able to know how to remove it and to understand whether you have removed it or not. So if you don't know what's in that environment, what's the point? And this is what the methodology behind it all has been right from the beginning to the end. We, I think, are the first people to have ever done this in a live environment. And it's just gone from strength to strength. I can show you the NEOS sampler, because this is what the clever guys, the scientists and professors and Andrew Conway Morrises and Vilas Nevaperkars of this world came together, and they they discovered this tiny little machine, this NIOSH tornado sampler, and they figured out how to use it, which is amazing. And that's where I'd like to hand over to Andrew, if that's all right. I've got a couple of other things that I'll and pictures that I can show you afterwards, if there's enough time.
That's great, Andy. Thanks. And no one would ever know this was your first webinar. That was fabulous. So Andy, well, Andy Conway Morris, if you want to sort of share your screen, and then we should have time, I think, to come back for your last few slides, Andy T.
Okay, not a problem.
Great. Thank you very much. And thanks to Andy Turner. Well, I mean, thanks to Andy Turner, full stop, because as he said, this whole project came from his original idea, and really was the question that came, having what seemed like a plausible idea, that if we could pass the air through a high efficiency filter, that we could clean it in a way that we were all quite used to wearing, FFP3 masks and protecting ourselves as individuals, but could we make the wider environment safer? And so I got involved because I'm a colleague of Dr. Navaperkas and have an interest in the diagnosis of pneumonia, and particularly using molecular diagnostics, so detecting the nucleic acids of pathogens. And with Gordon Dugan and Stephen Baker from the University Microbiology labs, we've developed a number of diagnostic devices. And so really, I mean, the background, and Andy's given it really nicely, but essentially the problem we all faced with COVID-19 was that we didn't have enough negative pressure rooms to put all the patients with COVID-19 in. So they were rapidly overwhelmed, and we started cohorting them in general wards or in intensive cares. We expanded out of intensive cares and created these surge intensive care units with sort of hastily redeployed bits of kit and bits of staff. And obviously these are environments that weren't designed for the containment of a highly contagious airborne disease. And obviously early on as well, I think the full airborne nature of the disease wasn't entirely recognized. And those of us who worked in intensive care were very lucky, because it was thought that the procedures we were doing, intubation, bronchoscopy, mechanical ventilation, were aerosol generating. And so we were afforded a high level of aerosol protection with our personal protective equipment. Sadly, that wasn't afforded to our colleagues on the wards who were working with fluid resistant surgical masks. And so we were sort of going into this was coming in out of the first wave. We realized there were high rates of infection amongst staff, particularly in the red wards, and interestingly, not at all in intensive care, even though that we thought the most exposed. So we knew that it was possible to detect the RNA of the SARS virus, so SARS-CoV-2, in the air. And there was data to suggest that it was spread by aerosol, so airborne spread over long distances. And really the question was, if we assumed that SARS-CoV-2 was an airborne disease, which at the time of doing the study seemed a reasonable assumption, but hadn't been fully accepted by the scientific or public health communities, then if we could take the devices that Andy Turner had been talking about and deploy them, could we remove SARS-CoV-2 from the air? And could we prove that? Because I have to say, I think, I confess I was a skeptic too, and it was the potential we were going to have a box that sat in the corner that made us all feel a bit safer, but actually didn't make us any safer at all. Now, as I say, we know from sort of in-lab testing that in principle, HEPA filters and combination with UV sterilization should work well. But the question is, does it work in reality in a dirty clinical ward? And because we had a sort of interest in more than just SARS-CoV-2, we said, well, actually, it's more than just SARS-CoV-2. What else do you find in the air in hospitals? And could these filters take those away? So those were the questions. This is the paper that we published subsequently for those who want to read it in more detail. And this was the setup. So we had two wards that we set up in, two bays within two wards. So one was a surge ward. So this was taking patients who were on standard oxygen therapy, so just a face mask oxygen, or indeed no oxygen at all, but all with proven SARS-CoV-2. And the second unit was our surge ICU unit, which was not an intensive care unit beforehand. So we pushed the old day admissions unit out and took over a ward that was barely suitable for the purpose, but needs must. And in the ICU, this was in the second wave of COVID. So we had a mixture of invasive and non-invasive ventilation. So people who were being ventilated by tight-fitting non-invasive ventilation masks or continuous positive airway pressure, high-flow nasal oxygen, and patients who were intubated and on formal mechanical ventilation. And what we did was we took Andy T's cunning devices. So this, on the surge ward, we used the Filtrex, and on the surge ICU, we used the other device. And then these two asterisks here indicate where we put the air samplers. So these NIOSH air samplers that we had acquired from collaborators in the United States and had used in previous studies. And the idea of positioning these filters or these samplers was, one was next to the filter, so that the filter itself has, as we'll come on to talk, has quite a high throughput of air. So that would suck air in from the whole ward. And so we could test that here, the proximal one. And then the other question was, was the air just being cleaned and recirculated immediately around the filter, or in fact, did it cleave the wider air? So we placed a sort of far field one on the further side. And just to illustrate quite how pressured things were, this was a 5-bedded bay beforehand, and in the red there, you can see the 6th bed that was added midway through the testing period as we ran out of ICU beds. So it was a pretty desperate time when we were doing this study. And I think all the more remarkable that we managed to get it done, given all the other pressures that were going on. Anyway, so these are the devices. Andy's already introduced them. They are combined HEPA UVC devices, and they were set to run at 1,000 cubic meters an hour. And we ran them for 24 hours a day. And we estimate that the air volume cleans were about 5 to 10 air volume cleans per room. And then this was the study that we did. So it was a service evaluation, and we did essentially a kind of crossover trial design. So the first week, we tested the air on 5 days, Monday to Friday, with the filter off. We then turned the filter on, tested for 5 days, then turned the filter off again and tested for 5 days. In the meantime, when we were testing, we also had a control sampler that was kept in a sealed bag, just to make sure there wasn't contamination getting in the lab. There were 2 samplers on the ward and 3 in ICU. In the ICU, we had 1 at head height and 1 at bed height. But broadly speaking, we were doing the same testing in both units. So the tests that we used, we had a standard qPCR for SARS-CoV-2, which is similar to the diagnostic test that's used in the clinical laboratory. And then we had a high throughput PCR for 59 other organisms. So this is something that we developed from the pneumonia work. And here we were looking for bacteria, so a range of gram-positive and gram-negative bacteria, some mycobacteria, some atypical respiratory organisms, some fungi, and a number of respiratory viruses, including another sequence for SARS-CoV-2. So we sort of looked for SARS-CoV-2 twice. And this is what we found in SARS-CoV-2 on the ward. So in the week before we turn the filter on, you can see here that we're picking up SARS-CoV-2 RNA in the air on the ward. And it's mostly in what's called the medium tube, which is particles of 1 to 4 microns. So eminently respirable particles. And you can see that we're detecting them on every day. When we turn the filter on, poof, SARS-CoV-2 becomes completely undetectable. So pretty striking. I mean, it's, I do a lot of biology, and I usually need to do some statistics to prove I've got a result. With this, I mean, it's just, it's gone. Just absolutely striking. Really almost unbelievable. And the clincher was when we turned the filter back off again, the SARS-CoV-2 came back. So really striking effect of having these devices on the ward. Now, those of you who are familiar with PCR, and I think most of us have sort of become rapidly familiar with it over the last 2 years, will perhaps notice that the CT values, so this is the sort of measure of how much virus there is quite high. And that is, to be fair, it's pretty much at the limit of detection. For those of you who are not familiar, essentially CT values, the higher it is, the less virus there is, essentially. So it's sort of an inverse relationship. And 38 to 40 is pretty much the limit of most assays. Now, so you could say, well, how do you know it was there? Well, the key thing is it wasn't there on the days when the week when we had the filter on, and it also wasn't there in the control sample. So we are as confident as we can be that this wasn't just false positives. Now, when we had a look at the other organisms that we were interested in, so this was this 56 organism panel that I mentioned earlier, you can see here a very similar effect. So in the air on the week when we had the filter off, there's absolutely lots, and it's filthy stuff. It's not stuff you want to be breathing, you know, Candida, E. coli, Streptococcus, fungi, viruses. There's a lot of dirty stuff in hospital air, slightly disconcertingly. And then when we turn the filter on, again, it almost disappears. All we've got left is a couple of yeasts. And this is just that represented another thing. Now, this is the bit where the science gets a little bit annoying. The third week, when we turn the filter back off again, the samples are degraded. So we were able to do the SARS-CoV-2 assay, but we couldn't do the bacterial assay, or this pan-bacterial assay. So that's why week 3 is missing here, which is annoying, but that's life for you. We're not trying to hide anything. It's just the way it went. So the other unit we tried on was ICU, and here the results were quite different. And again, this is, I think, quite a striking result, but for different reasons. So you can see here in week 1 with the filter off, there's no SARS-CoV-2 in the air. Week 2, there's pretty much no SARS-CoV-2. We've got a single detection. We think that probably relates to a patient who was having a particularly unfortunate day of a lot of coughing. And then week 3, again, filter off, no SARS-CoV-2. A really striking contrast with the general ward. And we're pretty sure now that this is because of the stage of the disease the patients were in. So the reality is, although when we started out and we were pretty scared, to be honest with you, about doing bronchoscopy in these patients and intubating these patients, actually the reality is that those of us in intensive care who had the best PPE were probably, ironically, the least at risk, because the patients had moved beyond the stage of active viral replication and active viral shedding by the time they got sick enough to come to us. We didn't know that at the time, but you know, and this is just one piece of data that suggests that there's a lot more data around that corroborates that. Now, interestingly, however, when we looked at the bacterial and the sort of wider bioaerosol, it wasn't that this unit was clean. As I say, it was a hastily redeployed day of surgery admission unit that wasn't designed in any way to be an intensive care unit, and is the place I least want to go back to ever again as a clinician. But yeah, so the lack of SARS-CoV-2 there was not because the air there was already exceptionally clean. In fact, it was just as dirty as it was on the ward. It's the patients who were there weren't shedding it. But once again, the filters worked just unbelievably. You know, we go from this absolute zoo of organisms before we turn the filter on to turning the filter on, and it's massively reduced. So what we concluded from our paper is that SARS-CoV-2 RNA could be detected in the ward of a COVID-19, sorry, in the air of a COVID-19 ward, but was very rarely detected in the air in a intensive care unit. And it's not just SARS-CoV-2. In fact, the air in these 2 units, not particularly well ventilated units, was full of potential nosocomial pathogens. And we are confident that the combination devices that we were using, so it's HEPA UVC cleaning, can remove detectable SARS-CoV-2 from the air and also remove bioaerosol. Now, what I suppose we don't know is, first of all, which bit of that whole device is the most important? Is it the fan? Probably not. Is it the HEPA filter? Almost certainly. Is it the UVC irradiation? Again, we don't know precisely which bits are doing what, so we can only talk about the device as it is. We've obviously done this in single bays in a hospital ward. So could we do this in a larger setting? are there any adverse effects? So we did this as a service evaluation. It was not a randomized controlled trial. We didn't collect data on potential adverse effects. I mean, we've now deployed these devices, and Andy will tell you a lot more about that. And I don't think that anyone is objecting too significantly to them, but there are potential harms such as noise getting in the way in small areas and so forth. And of course, the $1 million question is really, does any of this matter? It all seems plausible, yeah, with SARS-CoV-2 RNA, which of course is just RNA. It doesn't necessarily mean it's viable virus. And all these other nasty pathogens that I've told you about. Surely taking them out of the air must be a good thing. Well, yes, in principle. And I think we lost equipoise in terms of deploying these in red areas in the hospital, having seen this data. But I can't hand on heart tell you that deploying these will definitely reduce infections. So we have a study going on at the moment in Addenbrooke's, not in a red ward because, as I say, we've lost equipoise, but that's been run by a colleague of mine, Matt Butler, who's a geriatrician. And we are doing this as a longer term study to look and see whether we actually get an impact on those nosocomial infections from these HEPA devices. So that's a study that's going to take a bit of time to read out. So watch this space, but not for a year or so. So yeah, massive team of people involved in this. I'm lucky enough to be up the front on the paper, but there's a huge number of people from a really diverse group. And I've never got to work with heating and ventilation engineers before. It's been a brilliant experience. There's been microbiologists, infection control people, clinical academics, non-clinical academics. It's a real smorgasbord of collaborators. And it's been an absolute pleasure to be involved in. So I'll hand back to Andy T, who'll tell you sort of what we did next. Let me just end that and stop sharing.
There you go. Andy, back to you.
Thanks. Yeah, so just to explain a little bit about the ventilation within hospitals. Some people may deem that ventilation within the trust is less than adequate in certain areas. But what needs to be understood is the ventilation was compliant with the prevailing standards at the time and not compliant with the modern standards of today. And this is just something that we need to take into consideration. A lot of these ventilation systems in the NHS were designed 40, 50 years ago. We as engineers try our utmost, try and bring them up to the current standard of the HTMO 301, which is the basic requirement for safe ventilation. It's a guidance within the NHS. Some of it's legal, but it still is a guidance. And the thing is, the trials were done in areas where we have majority of it is natural ventilation with a little bit of forced air. The air change rates within these both these environments were very low. And the thing is, what a lot of people need to understand is that air scrubbers do not create air change rates. They enhance the air circulations. Whereas there's quite a few people, I deal with on LinkedIn or wherever it is, who have got this understanding that, an air scrubber is the, it's the miracle to get rid of airborne bioaerosols, whatever. Natural ventilation and forced air ventilation that's been filtered properly is still a better option. If we had systems, if we had money to use UVC or far UVC or needlepoint ion technology, then yeah, we would try it, but it revolves around capital as well. Yeah. The other thing is there are a lot of people that believe that HEPA filters are sufficient to absorb the pathogens and the bacteria and the fungi. But within Addenbrooke's, we made the decision to use the double protection. Like Andrew was saying, is no one really knows what actually stopped the pathogens and bacteria from being put back into the air once the machines were on. But we just felt that we wanted to have the double protection, as these units are portable. We don't just install them into an area and leave them. Infection control dictates where the systems go, and we move them around. And if that's the case, if they just, it's just my opinion, and everyone's entitled to their own opinion. HEPA filters alone, I don't know what gets accumulated within the machines, what residue is left over. And if our guys are moving these machines between wards over rough surfaces, I don't know what's going to get dislodged. And then when they get turned back on, does any of that, those pathogens get pushed back into the air? I don't know that. But what I do know is that with the UVC light technology in them, there's no chance of that happening. And therefore, that's why we opted for UVC and HEPA filtration. The deployment is vital. Infection control, they play a pivotal role in the deployment of air scrubbers within CUH. Any type of engineering department that doesn't have infection control on their side is in trouble. Big trouble. If you've got infection control on your side, you're both on the same page, it's a breeze. Everything just runs really smoothly, just like it does here at CUH. We've got a fantastic infection control team, from David Enoch, Liam Brennan, Christine Moody, Rachel Thaxter, and the list just goes on. They're very open-minded and very experienced in their jobs. And so it's made life really easy. The logistics were I think it was on the 21st of December, we were told that we needed to have as many air scrubbers in the hospital before Christmas Day. We deployed, well, we got the quotations together, we got the single tender waivers together, and we had every single air scrubber deployed on the 24th of December, and that was 55. So a big thank you to the CEFM team, providing the finances, Corin Shelton, Ian Jackson, Claire Howell, Trish Marchant. They all deserve a mention, because without them, we would really be in trouble. And the thing is, I've had a matron come up to me, and we deployed some of these air scrubbers in rehab for stroke, and they have got absolutely no forced air ventilation, only opening windows, so it's natural ventilation. And in winter, to have these patients exposed to the cold air, it just isn't fair. So I deployed a couple of air scrubbers. I put them outside of the wards, and she came to me and said, these are absolutely amazing. Out of the 5 patients that we had that were COVID positive, none of the staff got ill, and neither did any of the other patients.
Andy, sorry, can I just break in? Because we're now at the point where the Oscars would be playing the music, because there's lots of really good questions, and we'd like to go into the question time, if that's okay.
Not a problem.
Okay.
I could go on for hours, like I said.
Well, I know you didn't thank your mother. We didn't get to that stage, but
no, that's all right. That's fine.
So I'm going to hand over to my my BESSI colleague, Professor Susan Meeke, who's going to handle the question and answers. But that was just fascinating, and it's lovely to hear it from you, and also the kind of the uncertainties that remain and the practical use. So Susan, please hand over to you. And I don't know if you want to introduce yourself as well, because you probably should.
Yes, hello. I'm Susan Mickey. I'm Professor of Health Psychology at University College London and Director of its Centre for Behaviour Change there. And that was inspirational, really, really important contribution. Shows the importance of having a champion who really pushes for getting something done, getting a great team together and having a can-do approach to developing and evaluating these kind of interventions in real life situations. And what's especially heartening is, going forward, we're just going to have to make places safer, whether we're talking about in hospitals, in shared public places, in schools and universities. We can't just rely on humans to keep distance. We need to make places safer so everybody, even those who are vulnerable, can get out and about safely. We've got a huge number of questions here, some of them quite technical. I mean, the first one was about whether you're planning to go on and try HEPA without the UV sterilisation. But I think Andrew, one of you, made the point about why the UV was really important, an important part of that. You're nodding, so is that right? Do you want to say anything? I mean,
no, that's
12, we've got 12 minutes for about 6 questions, so only take only very quick answers.
That's correct. That's exactly the way that we are going.
Okay, the next one, I'm going to rattle through these just so we can get through as many as possible. Was there any other existing HVAC or supply air operating in the ICU?
In that ICU, no. It was limited to extract, a bit of supply in some of the lobbies and extracts in the bathrooms, and that's it.
Okay, thanks. What concentration does CT40 correspond to?
That's a very good question, and one that's rather difficult to answer. Essentially, the CT value is that you can't equate them between different assays completely, and it's relatively difficult to go from a CT value to plaque forming units, which would be your standard way of measuring actual viable viral titers. So I think what we can say is your ordinary CT value in somebody who's infected on the particular assay that we were using. So if you're taking a nasal swab, you might expect a CT value of somewhere between sort of 23 and 30. Much above 30, sort of 34, 35 is sort of levels you might see in someone who's clearing disease. And by 38, it's pretty much at the limit of detection. However, we've got to remember that we're talking about a really small area being sampled in somebody's nose who's actively infected versus a huge volume of air. And those NIOSH samplers that we use have got relatively low air throughput. I think it's something like 6 liters a minute or something like that. And they're obviously trying to sample a whole thing. So I think essentially what we've got is a qualitative. It's either there or it isn't. And I wouldn't read too much into those CT values.
Okay. And sorry, I should have been saying who's asking the question. So next from Peter Knapp, recent studies indicate that pH maybe around 11 could be ideal for a droplet containing viable SARS-CoV-2. I wonder if forcibly changing the pH might reduce viruses.
That's a really good question. I think, it's really interesting. And again, I'm not an aerosol biologist. I have to emphasize, but there's a whole load of factors that influence both the size of aerosol particles, how fast they drop out of the air, and the viability of virus within them. And it is possible that changing any one of those factors may alter that. And I think that's one of the interesting things about seasonality. Is change in humidity and so forth influences how long virus can survive in particles, but also actually just how big the particles are and how fast they drop out of the air. And it's not just that it's winter time, so we're all inside because, in the summer we're all out in the beer gardens. It's more complicated than that. How practical it would be to alter the pH of a particle, I don't know. And one can see, I think, you know, there are, when we're trying to come up with interventions, we've got to find interventions that are practical, that are tolerable to people. And if we're even changing humidity, you know, can make a room really quite unpleasant to be in for any prolonged period of time. And may also have other unintended effects. So if you look at things like bloodstream infections, we know that bloodstream infections in hospitals go up in the summer. And that's probably because of changes in relative humidity. And so if you were to change that and reduce your risk of airborne viral spread, you may actually paradoxically increase your risk of catheter-related bloodstream infections. So we've got to be careful about this and what interventions we apply, and not just assume that they are completely harmless, although I'm relatively convinced that these HEPA filters are almost certainly harmless.
Thank you, great. And from Paul Linden, do you take account of the ventilation patterns when placing the filters?
Sorry, say that again.
Yeah, sure. Do you take account of the ventilation patterns?
Yes. Yes, we do. Yeah. I mean, it's difficult to understand the liters per second within all the different areas, but we, on the supply and the extract, we take that into consideration quite a lot.
Okay, great. And then Peter Carey says presumably regular maintenance of this equipment is essential and would have to be part of any wider deployment. And Ali Fretum also says how often they need filter change and or other maintenance.
Oh, that's a very good question, because we've with the deployment, we've got a company that does all our maintenance. The filter changes, we've changed the frequency, because originally it was every 6 months on the pre-filters. We're now doing them every 3 months because of the high volumes on footfall and the lint that's getting absorbed. But the HEPA filters, if we're changing a large unit from a different area to a different area, we will change the HEPA filter and dispose of that, because we don't want cross-contamination. But the UV bulbs, we're changing them yearly as well. So, I mean, it's still ongoing, the experiments with these machines and figuring out how efficient they actually are. But yeah, we've reduced it down to 3 months now.
Okay, thanks. And Atlee also wants to know, how much do these cost?
They are quite expensive. You know, if you're buying them directly from the manufacturers, everyone's got a different price range. The Filtrix units, I think, with the service package are 5,800, and the MaxVac units with the filter package, because they offer a free first year of maintenance, they're about 4,100.
Okay, that's helpful. Yeah. Good. And next one from Matthew Butler. Quite a long but a good final question, given we've just got 5 minutes left. Can I first add my personal thanks to Andy T for being the catalyst of the Adam Brooks air disinfection study, also called AirDS, having made the introductions to our supplier Air Purity UK. Excellent talk, both of you, and thanks for your contribution thus far to the study. I was wanting to pick Andy T's brains about one unexpected finding we have seen in our study, namely that the CO2 levels on the wards when the air filters are on massively reduce more than we can explain through mixing. Our hypothesis is that the recirculation and higher air velocities entrain more air. Is this possible, or do you think it is simply better mixing?
I think it's better mixing. I think it's very kind of Matthew to say that. But one thing that I can say is Air Purity UK have got absolutely amazing equipment. Their AI system is fantastic. I mean, I just think that better mixing is produces better results with for dilution. Dilution is key, and we know that within theatres. So better mixing, I think, is key.
Okay, thanks. Well, we've got through quite a lot of questions, and no doubt others may follow up with you directly. I hope that's all right with other questions. But before I hand back to Jeremy, I want to also just say how good it is to see this sort of evaluation. You know, I'm a clinical psychologist by background many decades ago, and we used to have what was called ABA designs, which is exactly what you did, plus the control. And these are really feasible kind of designs within real world settings. And I think I think this has been really inspirational in terms of both the fact that, you know, if there's a will, there's a way, you know, really getting the right people together, being persistent, being creative, just getting ahead and sort of doing enough of it so one's in a position to get funding, but also thinking through how do you translate activity into empirical evidence and knowledge. And I think these kind of designs, sort of time series analyses, step wedge designs and time series analyses also can be just powerful and can be done. These are things that can be done without RCTs, which can be really persuasive. So thank you, first of all, for this whole approach to science, applied, useful science has obviously already had a massive impact, but also coming on and sharing your experiences and insights with us. So with that, Jeremy, can I hand back to you to say something about the future of the webinar?
Yeah, absolutely. And I'd just like to add to Susan's comments. I mean, this feels like it's opening up a large area of research that needs to go on. Yeah, we have this focus during the pandemic, but a lot of these things are things that could be studied more broadly, and to understand how things like room architecture or other ventilation sources or other factors might influence this. I think there's a whole range of methodological issues. I noticed the particle test, there was something like 20 observations in a room, whereas when you were doing the test in the rooms, you had 2 observation points. And so there's probably some really interesting methodological work about, well, how many do we have to do this, and can we start to standardize what would be a good core outcome set to do it? So it should spin off in many different ways. And what I hope is we don't end up putting it down until we have a next outbreak and then get very excited, as opposed to this is something we're learning now. So just to the two Andys, that was absolutely spectacular. That was what we were very interested in. Oh dear, I was trying to share my screen to tell you about the next one, and it seems to have done something weird. Oh my goodness, I am having a very bad day on this. So let me.
I can say something about the next one, Jeremy.
Please do, Susan.
I don't know if I can share my screen.
I'll keep working on my screen. Okay, if you've got it, that's good.
Okay, it's on. The next one's Tuesday, 5th of April. I think is that right?
Yep.
Yeah. Okay. And this one is lessons learned for increasing the impact of behavioural science advice on government policy. And we have Dr. John Kinsman, who's from the European Centre for Disease Prevention and Control, and has looked at the impact of behavioural science advice across many different European countries. Also, Professor Marijn de Bruin, who's been advising the Netherlands government, and myself, who's been advising the UK government, really to look at what sort of advice, with what sort of impact, what have been the barriers to translating the evidence that we know is very complementary to what we've heard about today, is going to be effective in terms of enabling people to change behaviour to protect themselves and others, and what's stopping that actually getting into policy and practice. So do spread the word through social media, through your networks, etc., and hope to see as many of you as possible on that date. And now I shall hand back to Jeremy for a final word. Jeremy.
Great, thanks a lot, Susan. I've put just in the chat box basically how you can get in touch with us. We're very keen to build this community of people interested in any of those behavioral, environmental, social and system interventions. And I think also one of the issues is clearly interactions, because there'll be social factors that might influence how things like the ventilation work might have an impact on that. So we'd really love to hear from you if you want to sort of get involved or just help us to spread the word. And also sort of thinking about this isn't about the pandemic, it's much broader. This is about these interventions for infectious control, whether it's sort of seasonal flu, intermittent outbreaks, or God forbid, another global crisis. But thanks a lot for today. To both Andys, that was very inspirational from both the sort of the, with due respect to Andy T, sheer bloody-mindedness of you and your enthusiasm, and then also the science as well. So that was lovely. Thanks a lot, and hopefully we'll see everyone next time. And the two Andys, if you want to stay on for 2 minutes, that'd be great as well.
Okay, thank you.
No problem.
Bye.
Thanks. Bye, everyone.